So as introduced, my name is Sae Dieb, and by no means this Dieb is the same meaning as the German language Dieb. It's just a coincidence. I belong to the National Institute for Material Science, and today I will be addressing this topic I have been working on about creating a visual research topic map for Samurai Catalog. And also at the end, I would like to briefly introduce the materials data platform DICE at NIMS. So this is the contents of today's talk. I will be putting more details on what I contributed more, which is the visual research topic map creation. For the DICE, DICE is a large platform containing several services. So probably I will not be able to go into details for all the services. I would just like to introduce briefly what kind of services and how to use them, and what kind of services that are free, and some are only internal used for NIMS people. So this is a brief introduction about me. Like I think Dr. Shawaf mentioned that I have a PhD in information science from Hokkaido University, Japan. At that time, I used natural language processing to extract experimental settings for nanocrystal device development from research papers. And then I moved to have a postdoc in the University of Tokyo. At that time, the topic a little bit changed into developing new machine learning methods for materials inverse design, like namely Bayesian optimization and Monte Carlo research. Then I moved to NIMS in 2018 as a researcher, where I worked on both sides, like I'm doing now the data and text mining thing, and also the materials inverse design, machine learning, data-driven based materials inverse design. I think some of you are already familiar with NIMS, but for those who are not, let me briefly introduce NIMS to you. NIMS located in Tsukuba. Tsukuba is a science city because it has so many national research institutes in Japan and also other institutes, and also has a good reputation university, Tsukuba University. It's 50-kilometer northeast of Tokyo. And NIMS itself was established in 1956 with a budget over $200 million and about 1,500 staff, half of them are researchers, and 3 campuses in Tsukuba. Within NIMS, in 2017, the Research and Service Division of Materials Data and Integration System was established in order to develop the data infrastructure to support materials innovation. And within it, the Data Platform Center was established to manage and create this infrastructure and maintain this infrastructure. Within NIMS, this is the distribution of how researchers are distributed over the field, several fields, our subfields of material science, from structural materials, magnetic materials, computational science, and so on. So now I'd like to move to talk about the main topic of today's talk is the visual research topic map creation for the Samurai Catalog. And first, I'd like to acknowledge the contribution of my collaborators for this particular project. And these people all belong to NIMS with different expertise on different skill set. So what is Samurai? Now, Samurai is a directory service for NIMS researchers. It contains profile page for each researcher with his or her own publications and some information about him. And these publications are linked through the DOI to NIMS institutional repository and digital library. NIMS contains storing several, NIMS has agreement with several publishers and stores a large collection of papers in XML format in its digital library. And this digital library is linked with each researcher's publication through the DOI. Recently, Samurai was even developed further with a unique ID for each researcher that connects him or her to external databases like Kaken database in Japan and the ORCID database outside. So the motivation for this project is to take this work, Samurai work, a step forward. So Samurai aims originally, to promote NIMS research activities to the public. We wanted to simplify this process by visualization of this research output for each researcher. This will maximize their information absorbance for the general public first. And second, it can capture the research trend for each researcher and promote potential collaboration within or outside NIMS. So we were thinking about why don't we summarize the research output for a researcher instead of reading this list of research papers or contributions. A general person might not attract the attention of a general person. We can just have a simple image that represents the total output of a researcher. And then from there, we can create a map that connects different researchers using the shared topic between these people who are working on like shared topic. So this is an overview of the method used in this work. I will be going into details for every step of this framework. So we collected large collection of XML format research papers from NIMS repository and then extracted sections like title, keywords, and abstract, tokenized these sections. We also used domain knowledge resources. In our case, as you know, like compounds, chemical formulas, formula play an important role in material science. And some researchers even specialize in certain type of developing certain types of compounds. So because of that, we introduce rule-based chemical compound extraction system, and then we use dictionary for measurement-related terms. Okay, and then we did the basic NLP schema, which is like tokenize and then reducing the noise by removing stop words, by removing numeric punctuation marks, and so on. Then we did frequent term analysis to extract the most important or representative keywords that represent the researcher output. And then we make a vector, we construct a vector from all these keywords that we collected. These vectors now represent the total output of the researcher within his work. And then this is visualized, and then by using some similarity metrics, we were able to conduct to calculate similarity between all these vectors that represent researchers, and then find the potential or be able to introduce potential collaborators using certain topic keyword for each one of them. So I will be going into more details for each step. So for the data collection, there was like around 1,000 members of Samurai data, the catalog. And then we were able to collect around over 8,000 published articles in XML format. We only use 3 sections: the title, the keyword section, and the abstract of the paper. We did tokenization. Tokenization means, maybe you are familiar, but it means just segmentation of this text using the general English language schema. We remove the numeric values, punctuation mark, filter the general language stop words like but, he, and, or something like this. Physical units also were removed because they don't have any meaning by themselves. And then we got a series of tokens for each paper, not for each researcher, but for each paper. The next step is that we believe that this tokenization schema will have low matching ratio if we think about the domain-specific knowledge or domain-specific terms. Because of that, we use this rule-based chemical compound extraction system, and for more chemistry-aware tokenization to capture chemical compounds. And then also we use a digitized version of the Japanese Dictionary of Physics and Chemistry to collect measurement-related terms, and like X-ray, diffraction, simulation category terms, and so on. So this will increase the matching ratio between the domain-specific knowledge and the text itself that were extracted from these papers. This is a table represent the number of terms that were extracted from these collections of papers. So we have about around over 100,000 over 100,000 terms. Of them, 5.5% of terms were chemical compound. They were extracted by this rule-based system, and then 0.2% of measurement-related terms. Around 15,000 are unique terms that were extracted, and 7.5% of them are chemical compound, 0.3% are measurement-related terms. And this is a look on the most frequent domain knowledge terms that we were able to extract from this collection. In both cases, chemical compound and measurement terms. So then from here, what we did is we have now 5 sets of terms and their frequencies that were collected from these papers. I mean, terms from title, terms from keyword, and terms from abstract, in addition to the chemical compound and the measurement related terms. Now, each set was assigned a weight within, we constructed a vector of all these terms, and using bag of word approach, and then each section or each set of terms was assigned a weight in relation to its importance of representing the research output. And then these terms were now visualized using the word cloud. In word cloud, you have larger font size for more frequent or more important term. These 3 examples represent research output visualization for 3 researchers. 2 of them work on magnetic materials and 1 of them works on measurement. So Mr. Hono and Mr. Sakuraba work on magnetic materials, and we can see that like Heusler, for example, Mr. Sakuraba is known for his work on Heusler. So we can see here spin from spintronics, magnetic resistance, or something like this. And in the case of Yoshikawa, Mr. Yoshikawa works on measurement. So we can see X-ray, surface, interface, band, or photoelectron, or something like this. Of course, I believe there are some terms that might not be relevant. They also appear here, but this is not perfect. We are still working on this, developing more and more of this system. So the next step is we define the similarity matrix. We just basically take the cosine similarity, and to measure similarity between the vectors we constructed for each researcher. And then researchers with high similarity can be connected. We draw a map, we visualize this map that use each researcher and researchers with high similarity to him using certain topic. In that case, Sakuraba is for example, the magnetic is connected with Mr. Nimori or something like this. Mr. Yoshikawa is connected with surface to Mr. Yoshiyuki. Okay, so something like this. Each researcher now in his profile in Samurai catalog can have this function. He can view, or she can view her visualization, her research output visualization in the word cloud format, and then she can also view the map that we draw. We believe that this will encourage collaboration, because you know now who works on what kind of topics. Okay, so after we done this, we wanted to do some analysis on the evaluation of this system. We did several types of analysis. At first, we wanted to study the effect of the author's order into the visualization of his research output. So generally speaking, when researcher is the first author of the paper or the corresponding author, that means this paper is more representative to his research or his topic than when he is a second or a third author. And to verify that, we conducted experiment using same researcher, first with the total number of publications that he is affiliated to, and then only with the publications that he is either first or corresponding author. And we can see here, for example, this kind of compound, for example, has a higher frequency for this researcher. So there's still some difference. It might not be, it depends on the researcher himself or herself to be, this difference might be significant or not, but still there is the difference depending on his position in the authorship of the paper. Okay, that's the first thing we did. And then now we want to study the effect of using domain knowledge resources. As we discussed before, we use these domain knowledge resources because we believe that general tokenization schema will result in low matching ratio with the domain knowledge terms. Because of that, we included this domain specific resources. And for example, this case, we compare the word cloud visualization for the same person using domain knowledge resources and without using it. And here, as you see, there are some chemical compounds to be found and also measurement terms that cannot be found when we did not use the domain knowledge resources. So this can confirm that domain knowledge resources in such cases is important to be used in material science. Okay, then the next and most important thing is we want to verify these researchers that we connect together through this map, through this topic map, they are really correlated in reality. Because of that, we designed an experiment to perform clustering on the researchers' output, on the vectors we constructed for each person. And we use two kinds of clustering method, the K-means clustering and the agglomerative clustering, which is a hierarchical clustering bottom-up approach. In this case, probably you are familiar with K-means. K-means try to cluster in data points into K clusters using the closeness, how much the data point is close to the centroid of the cluster. But the agglomerative clustering, it considers each data point as a cluster by itself and then try to merge two data points at a time, going up using their closeness or their similarity into one cluster. So merging while you are going up, it merges two data points at a time. So this is the performance for K-means and agglomerative clustering. Of course, this shows that there are two groups of people. Because we selected people working in two different research centers inside NIMS, then definitely we are looking for two clusters, but this cannot tell us anything. We need to evaluate the quality of the cluster itself. So to evaluate this quality, we use two kinds of metrics, the internal evaluation metrics and the external evaluation metrics. Internal evaluation usually refers to evaluation of clustering without knowing the ground truth label of the data point, meaning without knowing what is the actual group that each researcher belongs to. For external evaluation, it compares our result to the ground truth label that we already know, because we know these people, which group they are belonging to, whether they belong to the same group or to different groups. So for the internal evaluation, we use the Davis-Baldwin index. Davis-Baldwin index try to minimize the distance between data points in the same cluster and maximize the distance between the centroid of the cluster of different clusters. This is the equation of Davis-Baldwin index. The sigma represent the average distance from all data points to the centroid of the cluster, and C represent the centroid of the cluster, N represent the number of clusters. And in this equation, you can see the lower the Davis-Baldwin index, the better. And in that case, agglomerative clustering performed better in our case. And then for external evaluation, we compare our result to the ground truth that we know about these people, about where they belong. And then we use the purity and adjusted rand index. The purity represent what is the likelihood that a single cluster contains a single class. And we can see that the purity was 0.92%, which is quite high. And then for the adjusted rand index, it tries to measure how likely the clusters are similar to the actual classes that these people belong to, the actual groups that these people belong to. And also the higher, the better. We got 0.70% with K-means algorithm. I think so far we can see that to some level, using binary clustering method, we could achieve some level of accuracy that these researchers that we classify them to be close to each other in research topics, or their vectors are very similar to each other using the cosine similarity, they proven to be belonging to the same research group, meaning they perform more or less similar, they are working on similar topics. Okay, so as a conclusion for this part of the talk, we use the NLP, natural language processing approach, to collect and analyze data from research papers in Samurai database in NIMS. And by this, we wanted to maximize the information absorbance for the general public about research trend and research output for each person at NIMS. What is he doing? And this will lead to promotion of his work and promotion of NIMS research activities. Additionally, we try to create this topic map to connect people from different, maybe a different group, but they are doing the same things or similar, or like, anyway, they share similar topics. And this will encourage potential collaboration. There are, I think, several things that we are planning to do to improve this work. First, I started investigation using of language models to detect topics instead of like, we do this collection of terms and do frequent term analysis and term frequency, inverse document frequency, and something like that. We would like to use the language models to detect topics. Language models are like, have proven to be very effective in several text mining tasks. Additionally, the tokenization efficiency still still needs some improvement, I believe, because there are some irrelevant terms that happen to be visualized while they are not really very relevant. Additionally, as we discussed, like we could add a weighing factor for the position of each person inside the authorship of the paper, first author or corresponding author, second author, or something like that. Then there is the idea of interactive evaluation and adjustment system where people can edit, like they can view the research output, their vector, basically their vector of term, representative term. They can edit, they can remove or add some new terms. They think it represents or they represent their work more. Additionally, in this work, we only use the research papers, but there are other resources of information such as lab notes. This is also, we are thinking to use these lab notes, analyzing and collecting, and first we need to transfer these lab notes into a machine readable format, and then use them also to represent the output of each person. Okay, so this would conclude my first section or my first part of the presentation. And now I would like to introduce the materials data platform in NIMS, which is named DICE. DICE is not an acronym. So it comes from the DICE has several faces, and DICE platform has several services, and you might be intrigued by either the data or the algorithms or the software. So that's why they named this platform as DICE. And it's planned to be expanded to Japan-wide services in materials data science. So it will not be only limited to NIMS in the future. So DICE contains range of services from creating and collecting data to publishing data. Like when I say creating data, means that a high throughput experiment data can be collected and transferred into a machine readable format and added them, I can add them to them metadata, so we can facilitate using this data for research, especially AI or data-driven research. And then also there is a human collected databases like MatNavi. I will talk about it in a minute. There is also the automatic collected data from research papers, like what I presented in the Samurai work. And then these data, since they are now transferred and structured into machine readable format, they can be machine readable and they can be used in several analysis systems and tools. Then once someone uses this data and come out with the result, he can publish a paper, or she can publish a paper about that. And then this paper can be also stored in NIMS repository or inside DICE. There's this material data repository system, which stores the paper itself, the research data, the presentation data, and so on. So this is an outline of how this DICE platform integrates all these services together towards a full-scale materials data research. So first we have these several types of data or several types of data collection, and then these softwares can be used upon this data to analyze or to come with a new result. And because this now, as you know, that data-driven material science is becoming very important, because of the impact that AI and machine learning can have on accelerating the materials innovation. Now, this published result using the data-driven science can also be stored in with metadata, of course, that can facilitate access and facilitate usage of these data. So some key concepts for DICE. First, quality of data. We have a single user, a single ID for all DICE services. So we know when and who and what kind of data was deposited and so on. There's the accessibility issue, the usability of data. There are several licensing ways of depositing your data. And then there's a tool inside DICE to transfer the data into machine-readable data set with metadata. The data, this DICE will be persistent for 10 years. The data will be there for 10 years, that's the contract. And then in addition, it has a research aiding functionalities, like, for example, this text and data mining platform. It contains a large collection of data set of publications where you can search for certain terms or visualize the information or metadata about this collection of papers. But unfortunately, this TDM platform will be discontinued from the end of March, will be replaced by material data repository. Okay, and here are some examples of services inside DICE. So the MatNavi, this is one of the largest databases of materials, probably, I think, one of the largest in the world for several kinds of materials. So there's a polyinfo, atomwork, for several and like polymer database. This polyinfo is manually collected data from research papers, and these databases are all free, provided that you need to have an access ID for DICE. I mean, you can apply for DICE ID and access password for DICE, and then you can apply for using any service of DICE within DICE using this ID of DICE. So these databases, several types of databases, basic property, and then engineering related database applications, and structural materials sheet, data sheet. These are all can be accessed for free, but you cannot download like in bulk. You cannot download large amount of data. It's prohibited. Then, as I said, like there is this data collection from high throughput experiment devices, and then IoT for some devices that cannot be connected to the network directly for security reasons. And we use this materials data conversion tool, MDAC, to convert this data into a structure format and with metadata. So it could be machine readable format, and then it will be deposited in the materials data repository. This is the material data repository. It hosts the papers, the presentation, the research data, and it can provide a full text search, and you can also download. But this material data repository is only available inside NIMS. This RDE is for structuring the data, like structuring experimental record. I think, yeah, we have already mentioned that. And this materials data conversion tool from like this style, just plain text into an XML format. So it could be used for machine readable investigation. And yeah, so that's just an introduction for DICE. But if you have any questions, I would be happy to discuss. And additionally, you can drop me an email anytime on this email. Thank you very much for listening. And yeah, that's it. Thank you.